nanohub.org.
Online simulation and more for nanotechnology.
Welcome back to week 1. We're now on module 5. Now in the last module, what I tried to show you was that if you started from our basic expression for the conductance, and the conductance was like Q squared D over 2T. This is the resistance, which is the inverse of that. If you start from that expression, which we had obtained in the 3rd module, I believe, and then use the idea that the time it takes for an electron to get from left to right, from source to drain, has 2 components, the ballistic component proportional to length and the diffusive component proportional to L squared. If you put that in there, then you can get the resistance, write the resistance in the form that I had stated back in module 1, namely this modified form of the Ohm's law, where to the length you have to add something like a mean free path. Now what I'd like to do in this module is kind of do this a little more quantitatively and obtain some results, which is up in the slide over there. And these are the results that we'll use in subsequent weeks, and we'll come back and refer to it. And so what I'd like to do is show you how those expressions come about. Now, for this purpose, rather than work with resistance, it's a little more convenient. You'll notice all those expressions are in terms of conductance and conductivity. In principle, of course, there's no problem really. As I said, conductance is the inverse of resistance. Conductivity is the inverse of resistivity. But it's just that when working it out, I'll now be switching from this resistance expression to the conductance expression. So conductance then would look like the inverse of this. And now, for this time, I'll put in this expression that we had written before. It would be something like so what I'm doing now is just using the diffusive part of it to get an expression for the standard conductivity. That is, if you had a long conductor, so the ballistic part didn't matter, then the conductance would be given by what I have written there. Now, of course, I could have written the ballistic one also here. It's just that makes the algebras a little more complicated. So what I'm really trying to get is an expression for conductivity that you could use for big conductors. Right? And we know, of course, we have seen earlier that when you include both, the effect is to kind of add a constant term to this that we have seen before. Okay. Now, so if you just write the diffusive part, then you see you get something like this, and you could turn that around and write it as so the conductance then, it looks something like that. Now if you want the expression for conductivity, then the point to remember is that just as resistance in Ohm's law is given by rho L over W, conductance is given by conductivity times W over L. That is, conductance is the inverse of resistance. When I take this and invert it, it's W divided by rho L. So when I invert that, I get W divided by rho L. and the inverse of rho, inverse of the resistivity, is this conductivity. So you could write it in this form. So what we have here is an expression for conductance. So if I want the expression for conductivity, what I should be doing is conductivity should be conductance times L over W. So from this expression for conductance, what we obtain is an expression for conductivity, which is G times L over W. So when I multiply that by L over W, you see D over L square, and then I have to multiply with L over W. Then there's the D bar. So you'll notice one of the L's cancels. So I could write this as So this is then the expression for conductivity for diffusive transport. That's up in the transparency in the slide there on the left hand side. So what it says is conductivity is Q square, that's the charge on an electron square, times density of states per unit area. We have been discussing in terms of a two-dimensional conductor. If it was a three-dimensional conductor, it would have been density per unit volume. So it would be L times A, the cross-sectional area, whereas this is a two-dimensional conductor, so we have W. So that's density of states per unit volume, and as you know, that's a material property. In other words, I could take the conductor, make it twice as long, twice as wide. This quantity would not change. Why? Because if I made it twice as long or twice as wide, so the area became doubled, the density of states would also double. Something twice as big has twice as many states. So that ratio is a material property when it gets to big things. And then there is this D bar, which is the diffusion coefficient. So this is this expression for conductivity that one could use for large conductors. See? And it all came from this, our description here, this approach. And some of you may have seen a different expression for conductivity, which is what you usually see in freshman physics texts. That's the one usually remembers. It is something like this. Looks like sigma is equal to Q square N tau over M. So this is the expression that you'll often see in freshman physics. And I'll explain a little later. We'll discuss actually the relationship between these two formulas. These are two very different formulas. See, the expression for conductivity that we just obtained and this expression which is often called the Drude formula. And one important difference is here, of course, you'll notice conductivity depends on N, which is the electron density. And the point I've tried to stress from the beginning, that conductivity actually really doesn't depend on the total number of electrons. It only depends on the density of states right around the electrochemical potential. And that is very apparent when you look at this formula, that conductivity depends on the density of states around the chemical potential. Whereas here it looks like it depends on the number of electrons. And the thing we'll do next week is I'll try to compare the two and show under what conditions those are equivalent. As we'll show, there are certain cases where these two will give you much the same answer. But the thing is that when they don't agree, this is really the correct one. And this is not a new formula. This is well known actually. Well known meaning well established. It's just not something you usually remember. And the reason is, like, if you take a standard text in solid state physics, you will see both formulas, the Drude formula and the one we just obtained. It's just that this one, like if you take Ashcroft and Mermin, a standard solid-state physics text, this is in chapter 1. You can't miss it. This one is in chapter 13, way later, after many advanced concepts have been discussed. Because in the usual way of thinking of big conductors, it takes advanced formalisms like Kubo formalism or Boltzmann formalism to actually obtain this expression for conductivity. And so it comes in chapter 13. And so the net result is, this is not the one that usually people carry in their head. When they try to think of things, they try to use this. And the point I'll try to make next week actually is that this one is a much more general one. And one nice thing about the viewpoint we took here, that's this bottom, what we often call the bottom-up viewpoint. And that is, start from small conductors and then work up to big conductors. What it allowed us to do, this viewpoint, is it allowed us to obtain this result essentially in chapter 1 itself. We didn't really need any advanced formalism. We had fairly elementary discussions that gets you there quite quickly, you see. And this is something I'll talk a little more about in the next module, how this bottom-up view works and why it leads to profound results like this relatively easily. That's the part I'll try to explain better in the next module. But right now, then, the point I wanted to make is that this discussion that we went through, it gives you a fairly straightforward way of obtaining an expression for conductivity in the diffusive regime. And of course, the additional thing it gives you is the thing on the right-hand side of that slide. That is the ballistic conductance as well. Because in the usual treatment, when you talk about diffusive conductors, you wouldn't quite know how to handle a ballistic conductor. But what I'll try to explain is the ballistic answer also comes out fairly straightforwardly. So let's talk about the ballistic conduction. So the way you'd find the ballistic conduction would be something like this. So let me write the result we just obtained. That's for diffusive conduction. And now we want to write the ballistic conductance. And the way you find the ballistic conductance is that for this time, do not use L square over 2D, but rather we should use the L over the average velocity. As I said, that's much easier thing to write down. So this is the ballistic conduction. Time is just length divided by the velocity, the average velocity. And this you could write as, if you turn this around, as so that is the ballistic conductance. See? Now, one thing to note here is that earlier I had said that you could modify Ohm's law to look something like this, which kind of is useful in seeing that in the that when you go to a ballistic conductor with L almost going to 0, the resistance does not become 0, but instead there is a constant term there. But what is a little misleading about that is when you are talking about a ballistic conductor, really mean free path doesn't mean much. Neither does the resistivity, but the product actually means something. So in other words, what we just wrote down here as the ballistic conductance, that's of course the inverse of the ballistic resistance. So in other words, the ballistic resistance would be rho times MFP over W. So what we have just written down is kind of like W over rho times mean free path. What we wrote there. It's kind of like that. And although these two things don't mean much, point is the product means something. And what does it mean? Well, it's basically this quantity here. This is a very important thing we'll talk more about next week. It's the density of states times the average velocity divided by 2L. Density of states, as you know, is proportional to the area of the thing. So this is proportional to WL. There's an L here, so L cancels out. So overall, the ballistic conductance does not depend on the length of the conductor, just depends on the width. And one of the things that I'll go over in the tutorial lectures is how you find this average velocity. That is, as I had mentioned before, that in any conductor you have these electrons going off at different directions, and what matters is their velocity in the direction from source to drain, what you might call the z direction. So what you want is, when you write u, what you really want is the average velocity in the z direction. And how you find that average, that takes a bit of algebra, but that is where I'll be going through in one of the tutorials, and the answer is given up there, that this u bar is like the maximum velocity, assuming that it has some velocity v, but distributed over angle. Then when you do the angular averaging, you get an answer that depends on how many dimensions you're averaging over. Namely, if you had just a simple conductor, one-dimensional conductor, then of course there is only one direction, nothing to average. So in that case, it's just v. And I've written there these three numbers, and the three numbers up there refer to what you get in a one-dimensional conductor, two-dimensional conductor, and a three-dimensional conductor. That is, if you average over 2 dimensions, you'll get this 2 over pi. And if you average over 3 dimensions, you'll get a half. 3 dimensions meaning if you had a 3-dimensional conductor, so you have not only things going at different angles in this plane, but also at different angles in this plane. So if you did all that averaging, you'd get a half. So those are the three results, this 1D, 2D, and 3D. Okay? And that, of course, is not meant to be obvious, but this is a part of one of the homework problems, which I'll go over in the tutorial. Okay. So this is then the ballistic conductance. It depends on density of states, depends on velocity. And as we'll discuss further, actually, this is a quantity that's has a name to it. It's called the number of modes. Actually, this is defined as number of modes divided by the Planck's constant h, and has a special significance, as we'll discuss next week, in terms of the quantized conductance of ballistic conductors. But I'm kind of getting ahead of myself. The point I want to make here is that this is a material property, something that, just like density of states, there is this concept of a density of modes. And when you write it as resistivity times mean free path, it's slightly misleading, because as I say, the total thing is independent of any scattering, any mean free time or scattering at all. This is a ballistic conductor. Okay. Now, one other thing that you can do is, we have this expression for conductivity. So question is, could we write the conductivity in terms of the ballistic conductance? So could we write this as GB times something? And that's the expression that's given there, the third one. And let me explain how we get that. It's like that something is equal to sigma divided by GB. Right? So what you get is, the sigma is Q square d over WL times this diffusion coefficient, and then that's divided by GB, which is Q square dV over 2L, and then a numerical factor, which in 3 dimensions is 3 different things. 1, 2 over pi, and half. Those are for 3 different dimensions. Now, the diffusion coefficient also kind of includes an angular average. And basically, it is, this diffusion coefficient is like v squared tau But again, the angular average gives you a different number for different dimensions. And here actually, the coefficients are very simple. It's just 1 divided by the number of dimensions. So in 1 dimension, it's 1. In 2 dimensions, it's a half. And in 3 dimensions, it's 1/3. So what I've written here then is the diffusion coefficient. And this. So now what you can see is, so the Q squared cancels out, density of states cancels out, L cancels out, okay. And one of the V's will cancel out. So what you get is so remember, I'm still trying to write conductivity as ballistic conductance times something, and I'm trying to figure out what that something is. And you can see that something looks like V tau divided by W, and then a numerical factor that depends on the number of dimensions. Actually, I think there's a 2 there, 2 V tau. There was this 2 from here. So when I divide 1 by 1, I get 1. For 2 dimensions is half divided by 2 over pi. So that's like pi over 4. And then there is the 1/3 divided by a half, which is 2/3. And if you like, we could take the 2 from here and put it inside. So it would look like 2 pi over 2 and 4/3. So this is the quantity, V tau times this, that we usually define as the mean free path. So mean free path is velocity times mean free time. The numerical factor though is somewhat arbitrary, but this is what we usually call the mean free path, or we write it as a lambda. So in terms of the result here, then conductivity is like ballistic conductance times mean free path divided by W. That is an expression also we'll have occasion to use later. Now one thing you might say, well, why didn't we just call V tau the mean free path? You know, why include this strange factor which again is different in different dimensions? Well, you could do that, but then what would happen is the modified Ohm's law, instead of looking like L plus mean free path, you see the way you have now defined it, the way the Ohm's law gets modified is to this L, you add a lambda, the mean free path. Now, if you had defined the mean free path without those numbers, then what would have happened is you'd get L plus some strange number times lambda, that strange number depending on the number of dimensions. Which one could do is just that it's more convenient to write it in a way so it just looks like L plus lambda, and then have the lambda take care of this factor. Okay? So those are the 3 equations then that's up in the slide, which we'll have occasion to refer back to. One is the expression for conductivity that we obtained. The next is the expression for the ballistic conductance. And finally, how the conductivity can be expressed in terms of the ballistic conductance. Because the modern view of the way to think about conductivity would be something like, hey, if I have a conductor and it's ballistic, then it has a certain conductance, which simply depends on the density of states and the velocity. And that product is what you call the number of modes. It's kind of like the number of, that's what really represents the lanes on your highway. And that gives you the ballistic conductance. And then the longer you make it, and then the conductivity in a long thing also depends on the mean free path. It's this ballistic conductance times the mean free path. So these would be the results that we'll be using next week. So in the last module for this week then, what I want to explain a little more is the overall approach here and how it allows us to get relatively difficult results like this expression for conductivity using relatively simple arguments.